This is AP Calculus Section 4.6 Notes. Today we are going to talk about optimization problems. And optimization problems are about using extreme values of functions, so maxes and mins, to optimize practical problems in real life. So things that we might want to optimize, obviously, in real life would be profit, capacities, things like that. If we're thinking about shipping containers, getting a maximum volume based on certain dimensions, or we're thinking about a business, obviously we're always wanting to maximize our profits and we have to offset our startup costs in order to maximize our profits, things like that. So whenever we're doing problems like this, our steps here, 1 through 6, are obviously read the problem carefully, more than one time. Underline important information, values you know you're going to need, things like that. Draw a picture to represent your problem. And then on your picture, if you can, assign labels to the variables in the problem, identify the derivative values that you're given, and then any derivative values that you might need to find. And then usually we have to do some sort of a substitution of one equation into another in order to get an equation in one variable. And then we need to be careful here. Number 5 is a caution. Do not substitute given values into the equation too soon. This should not happen until the very end. And then finally, we're going to use our first derivative to solve for either the maximum or minimum extreme value of the function, whatever it is that we're looking for. Example 1. A box with a square base and an open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. All right, so right here, we are trying to minimize the amount of material that's being used. So we're looking for a minimum. All right, now if we have a square box with an open top, let's kind of sketch a picture of what that might look like. Okay, I am a terrible three-dimensional drawer, but you get the idea. All right, so we've got these sides. It's a square base, and I'll call this side Y because it's different than X, and we know that we have an open top. And the information is that the box must have a volume of 32,000 cubic centimeters. So I know that the volume of this box is going to be length times width times height. So our volume here is going to be X times Y, or X squared Y. And we know that that has to be equal to 32,000. But my job in this problem is to minimize the surface area of the box. Okay, so let's write that down. Okay, so this is our job in this problem. Minimize the surface area of the box. Well, let's write an equation for the surface area. Now remember, the box has an open top, so we just have the bottom, which we know that the area of the bottom is going to be X times X. So my surface area is going to be X squared plus, and then we're going to have the 4 sides of the box, and the area of each of the 4 sides is going to be X times Y. All right, so right now we have a surface area equation, but the problem is, and that's the equation that we want to minimize, right? Because we want to minimize the surface area, so eventually we're going to need to take the derivative of the surface area equation in order to minimize it. But the problem is right now that surface area equation is in 2 variables, X and Y. And I want it to be in just one variable. So that's what that volume equation is for. It's going to allow us to do a substitution here for Y. So if we were to solve this volume equation for Y, we would have 32,000, make sure you don't drop a 0, divided by, X squared equals Y. So I can take this 32,000 divided by X squared, and I can substitute that into my surface area equation for Y. So that is going to make my new surface area equation x squared plus 4x times 32,000 divided by x squared. And then, of course, I can do some simplifying. I can reduce the x in the numerator with the x squared in the denominator. So my surface area becomes x squared plus, if I cancel 1x on top and 1x on the bottom, I'm just going to have 1x on the bottom. And then if I multiply the 4 times the 32,000, I get 128,000 over x. Okay, so here's my surface area equation. All right, so to minimize the surface area, we find the critical values of the first derivative. So that means we have to find the derivative of our surface area equation. So surface area prime, first derivative of surface area, is going to be 2x plus, and then in the second term, that's really 128,000 times x to the negative 1 power. So if I bring the negative 1 power down, that's going to be negative 128,000 x to the negative 2, which means over x squared. So here's my first derivative, and this is going to be equal to 0 when the numerator is going to be equal to 0. So I think what I'm going to do, just to make this a little bit easier, is I'm going to combine these two terms into a single fraction. So I'm going to make a common denominator. So if I want to put x squared under this term, then I'm going to have to multiply the 2x by x squared. So my surface area prime is going to be equal to 2x cubed minus 128,000 divided by x cubed. Oh, sorry, x squared. All right, so again, this is going to be, this equation is equal to 0 when its numerator is equal to 0. So I'll write that down. SA prime equals 0 when its numerator equals 0. So 0 is equal to 2x cubed minus 128,000. Let's solve for x. So if I add 128,000 over to the other side, then I'm going to get 2x cubed equals 128,000. Divide both sides by 2, and we get x cubed equals 64,000. And then take the cube root of both sides, and we get x equals 40. Okay? So that tells us that x equals 40 is going to be the optimum side for the length of the base in order to minimize the surface area of this box. Okay? So now, finally here, if x equals 40, then my y dimension, or kind of my height of my box, is going to be 32,000 divided by 40 squared. And when I do the math there, I get a y value of 40. So actually, to minimize the surface area, the best option is to make this box a cube, right? So that the length, the width, and the height are all the same dimension. And so the dimensions of my box would be 40 by 40 by 40. And if I wanted to, so this is the answer to the problem, okay? And if I wanted to check, which, you know, checking your work is always a good idea. So if I wanted to check, I could say, well, I know that my volume is supposed to be x squared times y. And I know that the volume that I started this problem with was 32,000. So 32,000 should be equal to 40 squared times 40. And when you do the math, it certainly is. Okay, so that's just a quick little check that we did do our math correctly, that x equals 40 is the correct answer to minimize the surface area of this box. Our second example is a completely different type of problem. It says, find the points on the ellipse, and then they give us an equation of the ellipse, that are farthest away from the point 1, 0. Farthest away from the point 1, 0. So picture in your mind what an ellipse looks like. And we don't have to sketch the exact ellipse for this particular problem. We don't need a picture to do this. Just picture an ellipse in your mind floating somewhere in the coordinate plane, and picture the point 1, 0. We're trying to find the points on the ellipse that are furthest away from that point. And so based on the shape of the ellipse, we would expect that there would probably be 2 points that both satisfy the furthest away criteria. But when we think about the point 1, 0 and then some other point located on the ellipse, and we're trying to find the point that's farthest away, we're trying to maximize the distance between 1, 0 and points on the ellipse. So let's write that down. This is asking us to maximize the distance between 1, 0 and points on the ellipse. So what formula do we know that deals with distance? Well, how about the distance formula? So we should use the distance formula. And here's our distance formula. D is equal to the square root of x minus x1 squared plus y minus y1 squared, all under that square root, okay? But we know one of our points, right? We know that like x1, y1 point, 1, 0. So let's fill that in, because that's going to change our equation a little bit. So that's going to make our distance formula equal to x minus 1 squared plus y minus 0 squared. And of course, we can simplify y minus 0 squared to be just y squared. So really, our distance equation is the quantity x minus 1 squared plus y squared. And so just like in the previous problem, we know that we're going to need to find the derivative of the distance formula, right? Because if we're trying to maximize the distance, we're going to take the derivative of the distance formula. And right now our distance formula has 2 variables in it, the x and the y. So we're going to need to do a substitution for y. Well, what we haven't used yet is the equation of the ellipse, which was given to us in the original problem, and that has x and y in it. So right now we are going to use the ellipse equation to substitute for y in the distance equation. I'm just going to say the D equation. All right, so our ellipse equation is 4x squared plus y squared equals 4, and I want to solve that for y. So first I'll subtract 4x squared, so y squared equals 4 minus 4x squared, and then I'll square root both sides. So I get y equals, and remember when you square root you get plus or minus the square root of 4 minus 4x squared. So I'm going to go ahead and I'm going to put that value in for y over here. And so when I do that, my new distance formula is x minus 1 quantity squared plus or minus the square root of 4 minus 4x squared squared. Well, what happens when you square a square root? It undoes itself, right? The square root and the squared cancel. And when you square something that's positive, you get a positive. When you square something that's negative, you get a positive. Whoops, I forgot my top on that square root there. So my distance formula in its most simplified form here, I'm going to have this, I still have this, I guess it's not its most simplified form. I still have x minus 1 squared plus, when you square that square root, you just get the 4 minus 4x squared. Well, now I'd like to be able to combine like terms underneath my square root, so I should probably FOIL out that x minus 1 quantity squared. And so when I FOIL that out, I get x squared minus 2x plus 1 plus 4 minus 4x squared. And then finally, if I combine like terms underneath that radical, I get that the distance is equal to x squared minus 4x squared is negative 3x squared. And then I have a minus 2x. And then I have a 1 plus a 4, which gives me a positive 5. Okay. So there is my distance equation in its simplest form. My next step is I need to find the derivative, right? Okay, always our goal here, to maximize the distance, find the critical values of the first derivative. Since I need to take the derivative of this, I'm going to rewrite the square root as everything inside in parentheses to the 1/2 power. So I'm going to say my distance equation is really negative 3x squared minus 2x plus 5, that whole quantity to the 1/2 power. So then when I take the derivative of that, my d prime is going to require me to use the chain rule. So d prime is going to be 1/2, and then you take the derivative of the outer at the inner. So everything inside stays the same. This changes to negative 1/2, but then I have to multiply times the derivative of the function inside. Derivative of negative 3x squared is negative 6x. Derivative of negative 2x is negative 2, and derivative of 5 is 0. Okay. So there's my derivative. I can certainly clean this up a little bit. So my numerator is going to have the negative 6x minus 2. And then the 1/2 in front of the parentheses, the 2 goes on the bottom. And then everything inside the parentheses to the negative 1/2 power, that's going to be in the denominator under a square root below, because I'm moving it downstairs and making it to the positive 1/2. Okay, and then I could do one more thing. I could certainly factor a 2 out of the negative 6 minus 2 in the top, and then I'd have negative 3x minus 1. And the only reason that I care to do that is because then I can cross out that 2 with that 2. And so now I end up with negative 3x minus 1 over the square root of negative 3x squared minus 2x plus 5. Okay, so now that I have that, it looks a little scary with that square root in the bottom, but remember, if we're trying to find the critical values, we're going to set this derivative equal to 0. And again, a fraction is 0 when its numerator is 0. So d prime equals 0 when its numerator equals 0. So with that said, that means that I'm looking for where does negative 3x minus 1 equal 0. Add 3x to both sides, divide by 3, so we get x equals negative 1/3. And then if x equals negative 1/3, let's plug that into y. Well, we knew from before that y was equal to plus or minus the square root of 4 minus 4x squared. So 4 minus 4 times negative 1/3 squared. If I do the math there, negative 1/3 squared is positive 1/9 times the negative 4 is negative 4/9. So y is plus or minus the square root of 4 minus 4/9. And so then if I turn 4 into ninths, that's 36/9 minus 4/9, which is 32/9. And I can certainly simplify that because the square root of 9 is 3. And I could break 16 apart I could break 32 apart into the square root of 16 and the square root of 2, which would be 4 square roots of 2. So I get y is equal to plus or minus 4 square roots of 2 over 3. So again, remember in the beginning of the problem, we said based on the shape of an ellipse, there should probably be 2 ordered pairs that are equally far away from the point 1, 0 that both lie on the ellipse. And those 2 ordered pairs that lie furthest away are negative 1/3 positive 4 square roots of 2 over 3 and negative 1/3 negative 4 square roots of 2 over 3. So let's write that down. Points on the ellipse furthest from 1, 0 are negative 1/3 positive 4 square roots of 2 over 3 and negative 1/3 negative 4 square roots of 2 over 3. Sorry, that's so smushed there. Okay, so there's the answer to our question.